This meeting is being recorded.
I'm told to learn, and then subsequently evaluated as dependent training back. I argue that this has
Did you record it?
so we have to wait for the agent to actually data.
The only problem is that we might have difficulties, muting people on Zoom, like doing all this stuff. How are we going to do this? This is going to be a pain. Like, how can I just, mute participants? Because we don't have the app.
I can do that. Oh, maybe I might.
Yeah, if you could.
In this setting, timestamp numbers, single latency from requirement, an immediately learns that sample, and then it immediately put that on screen. The additional constraint is that the learner is going to allow us to pass through the data set unless it caches some data and loss of memory. As you notice here, we can still organize the data stream. Yeah. Similarly, we can still organize that data stream however we want, but the difference this is closer to what this is. Understand how the model is
That's all I can say. Yeah.
Hey, do you have your own intro slide for the session? Or should I leave my full screen sharing?
I don't think so. I think you can leave the screen sharing at the first. Yeah.
Okay.
I'll be posting, I'll be recording.
So our motivation for this paper really hinged on that idea of using those options.
Okay, I'll be right back.
Okay. Recording in progress.
Good morning, everybody. Can you hear me on the Zoom call?
Yes.
All right, awesome. Hello, welcome. It is so exciting to be here with you in person after 2 years away. Do we have anyone here who's here for their first in-person CCD? All right, whoa, okay, it's everyone, cool. Well, welcome. I was gonna say, keep your hands up and then anyone who's been here before should make sure to greet you. But it sounds like we all just need to be nice to each other today. So work on that. On the flip side of that, if anyone makes you feel unsafe or unwelcome, IEEE does not condone any bad behavior and neither do we. So please let us know right away. My name is Emma Alexander. I'm at Northwestern. I'm co-organizing this workshop with Tali Deckel from Houle and the Weizmann Institute. We also have Hassan here from now Peking University. And joining us later will be Ulugbek Kamalov from Washington University in St. Louis. Also shout out to our co-advisors in spirit, David Lindell at Stanford, soon to be Toronto, and Achuta Kadambi at UCLA for bringing the institutional knowledge of CCD through the pandemic so that we have something of a clue of how to run this workshop, even though it's been pretty different the last few years. So thank you all very much for attending. We are super excited to have you. And we're really thrilled to kick off with a talk by Vivek Goyal. He is known in the community for both his brilliance and his kindness. He's a strong mentor and advocate, and so it's really great to be able to showcase his work. He got his PhD in electrical engineering from UC Berkeley, a member of the technical staff at Bell Laboratories previously, a senior research engineer for Digital Foundation, and the Esther and Harold E. Edgerton Associate Professor of Electrical Engineering at MIT. He was an advisor to 3Dim Tech, winner of the 2013 MIT 100K Entrepreneurship Competition Launch Contest Grand Prize, and consequently with Google/Alphabet Nest Labs from 2014 to 2016. He's now a professor and associate chair of doctoral programs in the Department of Electrical and Computer Engineering at Boston University. He's a fellow of the IEEE and Optica, and his students have been awarded 10 IEEE paper awards, really impressive, and 8 thesis awards. He's a co-author of Foundations of Signal Processing, and today he's going to be telling us about quantization and dither in single photon LiDAR. So thank you so much, Vivek, for joining us. Take it away.
Thank you so much for that very kind introduction. Really sweet. I'm somehow not getting, after all this testing, my slide is not advancing. Why?
We had it advancing earlier.
I know, I was, well, okay. Today my talk, quantization and dither in single photon LiDAR. It's going to be a personal story because it represents introducing my first research love, quantization, to one of my more recent loves, single photon LiDAR. I don't want that to come across as just jokey. I think it's valuable for different members of a community to have different ideas central to their thinking. And quantization is central to my thinking. My first dozen or so papers, and then another dozen or so scattered in time, involve quantization and related ideas. Quantization theory is seen as part of the theory of data compression, but for me, it's extended outside of that to influence how I think about other parts of signal processing and even biases in human decision-making and psychophysical laws. And now it also influences how I think about single photon LiDAR. Before I get to the topic at hand, I want to give credit where credit is due. The students are the product. My PhD advisor said something like that to me about 20 years ago when discussing the academic research enterprise. And I mention that because many of the key works of my group involving single photon detection have the same student name coming up over and over, Rapp. This Rapp is Josh Rapp, and he was awarded the 2021 IEEE Signal Processing Society Best PhD Dissertation Award. All the work I'll talk about today is his. Specifically, I'm going to concentrate on surpassing timestamp resolution, which we hope has applicability beyond direct time-of-flight LiDAR. In DTOF LiDAR, we illuminate a scene with a short pulse of light, and the backscattered light is recorded by a detector. The amplitude of the returned echo gives a measurement of the reflectivity of the scene, and the time between the transmitted and received light gives the depth or range of the scene. In the single photon flavor of DTOF LiDAR, we use a detector that's sensitive to individual photon arrivals, such as a single photon avalanche diode, or SPAD. In single photon LiDAR, the laser is repeatedly pulsed and one builds up a histogram of photon detection times. The single photon sensitivity enables accurate ranging at long distances and fairly low laser power, or from weakly reflective objects. Now, I'd like to take you back to around 2014 or 2015. My group had done some well-received work on single photon LiDAR, and we wanted to extend that to the use of a SPAD array. We had a 32 by 32 SPAD camera from Politecnico di Milano with 390 picosecond timing resolution. And we had a 640 nanometer laser with 90 picosecond full width at half max pulses. To me, the root mean square pulse width is more natural, and that's about 38 picoseconds. And I'm going to always talk about pulse widths in terms of RMS length today. So is this equipment good enough to do something interesting? Well, the timing resolution of 390 picoseconds is coarse. Just how coarse is it? Well, if we multiply 390 picoseconds by half the speed of light, we get 5.8 centimeters. 5.8 centimeter depth resolution, it's pretty coarse for a room scale experiment, like imaging a life-size mannequin. It's coarse enough to flatten out all the facial features. So if we want to have visually interesting results, we need to do better than the timing resolution of the detector to get by with this equipment. Why does the detector's time tagging resolution limit accuracy? The exact time for a photon detection follows some probability density function that's centered at the true time of flight. But the detection time is recorded as a digital value based on a bin width of 390 picoseconds. The problem with this coarseness is that lots of different true times of flight map to the same digital value. Also, as illustrated here, I can repeat this over and over many repetition periods, and I get the same digital value. But this illustration is missing something. What if the spread caused by the laser's temporal profile straddles two bins or more bins? Then say I have 60 detected photons. They might be split as 10 and 50 over two neighboring digital values. And this becomes the basis to produce an estimate between the two digital values. If straddling multiple digital values is good, does that mean a larger sigma would be better? It might be a little counterintuitive because short pulses are usually considered a virtue. So it's a little like asking, do we actually want worse equipment? Maybe within reason. So we don't want extremely long pulses, but we do want the RMS pulse width to be larger than the quantization bin width. Here's specifically our study of this. When we used our SPAD camera with 0.39 nanosecond time bins, that's the 390 picoseconds that I mentioned before, we didn't want to use the native sigma equals 0.038 nanosecond sigma of the laser. Instead, we intentionally spread the pulses temporally to have sigma equals 1 nanosecond. The metric we used to explain that this was good was the fraction of pixels within 3 centimeters of the correct depth from 10 detected photons. 3 centimeters is about half of the 5.8 centimeters that we computed earlier. So accuracy finer than the detector's time bins is possible, and it can be optimized through the choice of this sigma parameter. To this day, I'm not really sure how innovative this aspect of the work was, and I'm happy to hear your comments about that. When we completed that earlier work, we were distracted with startups and whatnot, but around 2017 or 2018, I was back to academia and ready to understand these phenomena thoroughly. What we're doing here is adding noise to spread measurements over multiple digital values. So we can ask, is pulse broadening the best way to do that? And if we are doing that, are there estimators better than the sample mean? Let's define a few symbols. The photon detection time is x, which is the true time of flight mu x, plus a Gaussian variable z from the Gaussian pulse shape of the laser. What's recorded as a digital value is the rounding of x to the nearest multiple of delta. Pulse broadening is additional Gaussian noise. Instead of making it part of x, let's write that additional noise in the second line. That W is called a dither signal, a random variable added before quantization. So is this the best that we can do? It's not really a fair question to ask because we haven't set any rules of the game in terms of what we're allowed to do. But still, I'll say, no, that's not the best we can do. We're looking at dithered quantization, which has a well-established theory. It's better to have subtractive dither, which means to subtract the same quantity W after quantization. And it's better for the dither signal to be uniform over an interval of length delta than Gaussian. When I say should, I mean that we'll get better estimates of mu x if we change the type of dither that we use. So I'm claiming we should use subtractive dithered quantization. Is that physically realizable in LiDAR? Yes, it is. So conventionally, the laser driver provides the time correlator with a start signal at the same time as it triggers laser illumination. To add in a dither signal, we replace that direct communication with an external pulse generator that both triggers the laser driver and synchronizes with the time correlator. By changing the relative delay between these pulses, we can add or subtract perceived delays from detection time before the coarse quantization. Now, that I hope it seems reasonable that we can use subtractive dither, let's look at how to do the estimation. Suppose we have K detected photons. that means K of these recorded YIs. The theory of Dillard quantization tells us that each YI is mu X plus the Gaussian additive noise from the laser pulse plus a uniform additive noise where Zi and Ui are independent. Now, each Zi and each Ui has mean 0. So it makes perfect sense to use the collection of Yi's to estimate mu X with a sample mean. It's unbiased because of the Zi's and Ui's all have mean 0, and its variance is decaying to 0 as K increases. But let's again ask, is this the best thing that we can do? And the answer is no. To demonstrate the suboptimality of the sample mean, let's look at the sigma z equals 0 case. There's no Gaussian noise anymore, just uniform noise. Here, it turns out that it makes sense to use the sample mid-range as the estimator. So the sample mid-range is the average between the minimum and the maximum of the observed values. It's also unbiased, and its variance decays much faster with increasing K than the sample mean. It's an extreme case of the general improvability upon the sample mean. It's order 1 over K squared versus order 1 over K. The difference is not generally this extreme, but setting sigma z equals 0 really makes it easy to drive home that suboptimality. Returning to the general problem, which includes both the Gaussian and uniform noise, we have an overall noise that we'll call V. So we now have a model which we can analyze. We can find the best possible mean squared error through the Kramer-Rao bound, and we can compute maximum likelihood estimates. The plot here on the right shows mean squared error normalized by delta squared as the ratio between sigma z and delta is varied. On the left end of the graph, the Gaussian noise is negligible, and the mid-range essentially matches the ML estimate. On the right end, the uniform noise is negligible, and the mean essentially matches the ML estimate. Since the ML estimate does not have a closed form, Josh took this further. He found that the generalized Gaussian family is good for approximating that total noise V. The generalized Gaussian distribution has a parameter P that controls the decay of the distribution tails. P equals 2 corresponds to a Gaussian distribution, and the P equals infinity limit gives a uniform distribution. Depending on the ratio of sigma z to delta, there's a P value that matches the second and fourth moments. The figure on the left shows the generalized Gaussian approximations obtained by this kind of moment matching between the GG distribution and the true distribution of V. One value of this generalized Gaussian approximation is that existing closed form estimators can be used. The sorted observations, Y1 through YK, are called the order statistics, and shown here is an example of a closed form estimator based on the order statistics. Putting this all together, we get some performance comparisons and rules of thumb. There's a regime where the quantization is extremely coarse relative to sigma z. Because of that, the overall noise is approximately uniform, and the mid-range estimator is then nearly optimal. Notice there's really a sizable gain over using the standard sample mean estimator, right? The simple calculation I showed you was for the sigma z equals 0 case, where there's a 1 over K squared versus 1 over K difference. But even when the Gaussian noise is not completely negligible, there's still a sizable gain over using the sample mean. There's a middle range where the total noise is not well approximated as uniform or Gaussian. Here, you really should use the generalized Gaussian approximation, and you get a significant gain from using a non-trivial estimator. And finally, there's a regime where the quantization is fine relative to sigma. Then the total noise is approximately Gaussian, and a simple sample mean estimator is nearly optimal. In fact, you might as well not use dither because there's so little advantage from it. Okay, so we've had some fun with dithered quantization theory. At least I've had some fun. It was definitely inspired by single photon LiDAR, but is it just abstract nonsense? To understand that, we have to close the loop back to experiments. We saw that broadening an illumination pulse is good in an experiment. We understood pulse broadening to be a use of non-subtractive Gaussian dither. A well-understood, well-established theory tells us to instead use subtractive uniform dither. Based on the generalized Gaussian family, we found simple estimators that are nearly optimal. So can we demonstrate improvement experimentally? Our initial results were positive for the use of dither because of the reduction of the root mean squared error shown here. But they were negative for all the fancier parts of the work where we developed estimators that ought to be better. The poor performance is because matching the mean and variance gives to get a Gaussian fit doesn't characterize the laser pulse profile well. The sum of a Gaussian and an exponential is called an exponentially modified Gaussian. With just one additional parameter, we can use an EMG to get a much better fit to our laser pulse profile. And then what Josh subsequently found was that under an EMG model, the best linear unbiased estimator in our setting, where we have these subtractively dithered quantized measurements, is very complicated. The complications stem from lack of symmetry. The EMG being asymmetric breaks many of the nice symmetry properties of the order statistics. In particular, the covariance matrix of the order statistics becomes really complicated with a dependence on K, the number of detected photons. So Josh proposed and validated another remarkable simplification. It's to use a generalized Gaussian fit by kurtosis matching, even though this means fitting an asymmetric distribution with a symmetric one. It doesn't look like a great fit, but the right side tail, the heavier one, is matched well. And it turns out that that's what's important to having good performance. So you can then choose a simple trimmed mean estimator based on the generalized Gaussian distribution parameters, and performance turns out pretty good. For an experimental demonstration, we have this 3D mask to image. It's a different laser than at the beginning of the talk. So its sigma is 350 picoseconds. We set the time bin delta to 2048 picoseconds. We did a 45 by 45 raster scan with 6.15 millisecond per pixel dwell time. And with those parameters, we got 410 photon detections per pixel on average. Now, one deviation from the theory as I described it and the experiment that's actually done here, well, we can't have continuous uniform random variables for the dither because the dither has to be digitally controlled. So we collected data at 10 picosecond steps of the dither signal, which, again, it's a slight deviation from the theory, but not very significant. Okay. A proxy for the ground truth was collected with much lower delta, just 4 picoseconds, and many, many more photons per pixel. So we can reasonably consider that to be the ground truth. With the coarse timing described here, we get the depth map shown with root mean squared error of 82.1 millimeters. Now, I put the sigma z and delta values into distance units to try to understand this 82.1 millimeter number. If we approximate the timing quantization error as uniformly distributed between plus and minus 1024 picoseconds, this should give a root mean squared error that's 307 millimeters divided by the square root of 12. And that's 88.6 millimeters. Now, the 82.1 that we got as a baseline is just a little bit lower. This is because the sigma z being about 17% of delta is too small to get a significant benefit from the built-in non-subtractive Gaussian dither of the data collection, right? So we're kind of, roughly speaking, we're at that original setting from the beginning of my talk where I talked about having 390 picoseconds as the delta and 38 picoseconds for sigma, and how that's just not a good choice, right? You wouldn't get significant benefit from spreading your measurements over multiple digital values. Now, with the subtractive dither, as described here, we drive the RMSE way down. Dither with just the simple sample mean estimator gives about an 11 times improvement in RMSE. And if we also use a generalized Gaussian based estimator, including the EMG fit to the laser pulse profile rather than a simpler Gaussian fit to that profile, we get a further improvement to a 13x reduction in the root mean squared error. So I can summarize this part in a single sentence. Subtractive dither is an inexpensive way to surpass timestamping resolution. Now, since I have a few minutes to spare, I'll mention a second set of signal processing techniques for single photon detection, mitigating dead time effects. I wanted to include this today because it follows the same trajectory of satisfying theory inspired by real equipment, an unsatisfying experiment, more theory, and then a very satisfying experiment. All right, so in single photon LiDAR, after each detection, there's a fixed duration dead time during which the photons are missed. Now, I'm modeling here a free running mode that has the possibility of multiple photon detections per period. An important complication in this free running mode is the lack of independence across illumination periods. In the bottom plot, we see that the detection time histogram is distorted relative to the arrival time PDF, and the manner of that distortion is pretty far from obvious. Now, even though we have a lack of independence across repetition periods, the situation is not arbitrarily complicated. We've proven that the detection times in this model with detector dead times form a Markov chain. And the stationary distribution of that Markov chain is a good predictor of the empirical histogram. So this was a satisfying theory up through, doing detailed Monte Carlo simulations. But When we attempted to complete imaging experiments, we discovered that our equipment has electronics dead time longer than the detector dead time. So our elegant theory wasn't good enough. When the timing electronics have dead time that's longer than the detector dead time, the detection time sequence is even more complicated. In particular, it's possible for a photon to arrive before the electronics have reset, but after the detector dead time is over. Right? That's what's illustrated here. So there's a detector dead time and electronics dead time. When the detector has become active again, but the electronics are still dead, an arrival can be detected, causing a detector dead time, even though this event was not observable. So the whole thing becomes significantly more complicated to model. Some dead times are caused by unobserved events. It's much more tedious and messy, but we can once again show that the detection time sequence is a Markov chain, and we can get close matches between theory and experiments. So this is the basis for the final results that I'll show today. In the upper left, we have a ground truth proxy that's captured with some very large number of illuminations and no dead time effects, or no distortions or biases caused by dead time. Attenuated in the upper right means to obey the 5% rule. So in time correlated single photon counting, the 5% rule is this rule of thumb that if you have detections in at most 5% of the repetition periods, then the distortions due to dead time are negligible. Naive in the lower left is to just allow the biases that come from dead times. And our method on the lower right gives more accurate depth and reflectivity, and this significant visual improvement as a result, on top of the quantitative improvement. So it again followed this trajectory of needing more theory to make the experiments really work. And that's it for today. This work was a lot of fun, and I'm always looking for people who want to have a lot of fun doing research. If you're one of those people, reach out. I'm happy to pay for referrals with some combination of dumplings or beignet or sazeracs. Thank you very much. I'm not sure who's there right now. Okay.
Yeah.
Okay.
Can you hear me back? Thanks for a great talk. Emma.
Hello, sorry, sounds
Okay.
like we were, okay. Is this working now?
Yes.
Yeah.
Okay, perfect. Sorry about that. We love your talk. There was a lot of applause. You didn't hear it, but the room blew up. If anyone has a question, please feel free to come forward or drop it in the chat. Oh, perfect. I'm not sure.
Hey, Vivek, David Lindell, great talk.
Hi, David.
Congratulations to you and Josh on great work. I just had a question on the first project you talked about in the dithering case. I noticed the results were shown for k equal to 125. I was curious, when you have the number of photon detections dropping down, maybe even in the extreme case with a few photons, is it still worth it to use dithering, or how does that work?
That's a great question. So actually, these are definitely gains that are increasing as K increases. And I guess, so yeah, I guess they're, again, my slide advancing is behaving very strangely. So I didn't try to illustrate the variation of the performance with K. But let me point out a couple things. So one thing about the experimental results that I showed, they were not very far to the left of this graph. Sigma Z over delta was about 0.17. So in fact, relative to this graph, which of course is not, well, you know, this was for the slightly more idealized Gaussian case instead of the EMG case. But the experimental results, they're only kind of here, where the advantage from the more sophisticated estimator is not that huge. So we would expect larger gains, you know, with smaller sigma Z over delta. But the other, you're raising a great point about the significance of this number K. The advantages from the dither are increasing from larger K.
Got it, makes sense. And
and you can kind of see that from the limiting case, right? So many of my students over the years, they must think I'm kind of crazy by how inspiring I have always found this difference between the mid-range and the sample mean. So if we look at that very simple inspiration for this, then of course the K equals 2 performance is exactly the same, right? The mid-range and the mean are the same thing if K is only 2, and the gap has to, you know, increase as K increases.
Got it. Yeah, great. Thank you, Vivek.
Thanks.
All right, thank you. I think we have time for one more question. If anyone has one. I have a question. So I noticed these objects were, they were all pretty matte, and even with the mannequin, you know, you weren't dealing with like the subsurface scattering of skin. Obviously that's going to be a really challenging problem, but can you maybe give us a flavor of like either how it fails or how you might extend to those cases?
Yeah, I mean, so you're right. Here, I'm showing only results where we assume there's no change of the shape of the pulse from the reflection process. Actually, this is something we've been thinking about recently. We've been trying to develop methods to estimate surface normals based on how the reflected waveform does differ from the transmitted waveform. And that's not virgin territory. I mean, Julian Taquella did some really nice work showing that tilt angles can be estimated from pulse broadening. But we've been trying to build upon that. Yeah, it's of course not included in what I talked about here. There are all these different types of complications that can come up in single photon LiDAR. And I mean, it's fun to look at different combinations of them and see what kind of signal processing tricks can be brought to bear.
Excellent. Well, I'm sure we're all very excited to keep an eye on that and see what else your lab comes up with. Now that Vivek can actually hear us, let's thank him one more time.
Thank you.
All right, thank you so much, Vivek. And our next speaker is also virtual. Carola, I believe you are on the call. And if you want to start your video and share your slides.
Yes, hello, everyone.
Oh, excellent. Wonderful. All right, well, while you are pulling up your slides,
Can you see them?
Yes, beautiful. So thank you so much for being here. Carola is another really exciting speaker that we're very fortunate to have. So she's going to be talking today about some data-driven priors, which is a topic that I think many of us are very interested in. She's a professor of applied math at Cambridge. She's the head of the Cambridge Image Analysis Group, but she's also the co-director of the EPSRC Cambridge Mathematics of Information in Healthcare Hub. She's a fellow of Jesus College, Cambridge, and the Alan Turing Institute in London. She also holds the chair of the Committee for Applications and Interdisciplinary Relations of the EMS. She focuses on variational methods, partial differential equations, and machine learning for image analysis, image processing, and inverse imaging problems. She's very interdisciplinary. She works with a lot of doctors, biologists, and physicists, chemical engineers, plant scientists, artists, art conservators, a really broad application of some fundamental math. She's been awarded many, many prestigious awards and given many plenary talks at quite fancy applied math conferences. So we're super lucky to have her at our workshop today. Yeah, so she has her PhD from the University of Cambridge and is now a professor there. So thank you so much, Carola, for joining us. Take it away.
Thanks so much, Emma. It's a really, really kind introduction. And I'm very fortunate that you invited me. So thanks a lot. And maybe also, I love to have questions in between. If people want to interrupt me, that's great. I'm also going to set myself a timer because I'm usually not very good in timing myself otherwise. So if the clock rings, it's 32 minutes, which means I should be slowly wrapping up. Okay, so right, so I'm going to talk about data-driven image priors, in particular data-driven regularization within a variational models context for solving inverse problems. And I want to talk in particular about deeply learned regularizers. Yeah, and this has been a topic that has been keeping us busy for a couple of years now. And I want to share with you some of the results that we got and some of the insights. So why data-driven priors? Why data-driven regularizers for inverse problems? I think we have seen in the last maybe 5 years or so, really a lot of promising results at the interface of deep learning and inverse problems. And that in particular comes from the power, the capability of neural networks to capture information in data, which points really towards using these neural networks to model things that we usually can't model very well in inverse problems, which really is the prior information, okay? They only work in practice when combined with mathematical and statistical modeling. On the other hand, there are a lot of works out there in this context which really lack mathematical scrutiny. What I'm going to talk about today, so this learned regularizers, learned priors, you can see really as a kind of hybrid between gaining performance from neural networks by using them to model prior information, but then still stick to a mathematical framework in which we preserve theoretical guarantees for the solutions. And in the context of inverse problems, it's super crucial, right? Because these are usually ill-posed. And we did a lot of work in the past to develop regularized solutions which give us well-posed approaches. Yeah? So let's not let's try to preserve this. Okay, so what is an inverse problem? So in an inverse problem, we take measurements, usually noisy, imperfect measurements. And we are not directly interested in these measurements, but we're interested in something that is hidden in these measurements, that is connected to the measurements via what is called also a forward operator, capital T. Okay, so here's the equation. My measurements are little y. What I want to reconstruct, what I'm actually interested in is u, that is usually well represented by an image. And little n just stands for noise, random corruptions in the measurements. And then I have a forward operator, capital T, that in most of the things that I'm going to discuss and that will be affected by kind of what I'm discussing, you can think of as an integral transform. Okay, so I'm mainly going to talk about linear inverse problems where capital T is a linear forward operator. Okay. And here you see an example. This is computed tomography, where this capital T is a subsampled radon transform. Okay, so usually these measurements suffer from noise and also undersampling. And so what you measure is this here on the right is really in a very different space as what you want to reconstruct, which is an image. Okay, so the problem, the challenge in solving inverse problems is that they're typically ill-posed. They're typically ill-posed because of properties of this forward operator, because of undersampling. You have an underdetermined problem that you're solving, and then of course everything is attenuated if you have ill-posedness because of noise in the measurements. And so in order to solve them, we need to turn them into a well-posed problem that we can actually solve robustly. And we do this most of the time, we do this through regularization, and a very prominent way to do regularization and to solve inverse problems is the variational regularization approach. Okay, so here I'm just repeating again our model for the image. Let's just call this the image. Okay, so the image U that I want to reconstruct connected to the measurements. And so the variational regularization approach tries to find an approximate solution to this problem as a minimizer of an energy functional that usually consists of two terms. One is the term that captures the data model, okay, that quantifies that in a way. It's called data discrepancy or data fidelity term. And again, in a lot of cases, in a majority of inverse problems, this is modeled by a least squares fit between the measurements and the forward model. And then this is now complemented, and this is where the regularization comes in, with a regularization term, a kind of smoothing term that should model all the prior assumptions you have about the type of the type of images you want to reconstruct from these measurements Y. Okay, so in a way you can think about it like this: the problem, computing U from Y just based on this equation, is ill-posed in the space in which it is set, let's say in the function space in which is originally set. So what the regularization does is it's kind of making the search space smaller. It's saying we are not looking for U all over the place, because there could be many solutions there and many bad solutions as well. We are looking at a subspace that is now determined by this regularization, in which we can now robustly, maybe even uniquely, find a solution U to this problem. And a typical example for a regularizer, in particular in inverse imaging problems, is, for instance, the total variation that many of you, I'm sure, have seen before, that models images by assuming that they have a gradient which is sparse. Okay, so with an L1 of the gradient of U, and this basically results into kind of piecewise constant images where edges are nicely preserved and the rest is kind of approximated by a constant. And then we have this little regularization parameter alpha that balances those two things out. Now, the connection to the regularizer modeling a prior assumption also comes, by the way, from the Bayesian perspective. So you can also view this variational regularization approach as the map, as the maximum a posteriori estimator, where the regularizer here would be the negative log density, prior density. Okay. Okay, so right, so this is the setting. Now, as I said at the beginning, deep learning really had a huge impact of how people are solving these inverse problems. And this is in particular because knowledge-driven models such as, total variation regularization are really kind of limited by our ability to model images, yeah? to model structures and images that are important and that are kind of characteristic for these images. And so what you see here is just a teaser on, again, a CT example. This will, computer tomography will follow us throughout this presentation. where you again see the measurements, and you see three different reconstructions. Two kind of knowledge-driven ones. This is a filtered back projection. It's just computing the pseudo-inverse of this of the subsampled Fourier radon transform, and that you can think of as a kind of baseline unregularized reconstruction. The next one is total variation, and here you can see one example, which is one of our work examples. Okay, so this comes out of what we did, of a deeply learned reconstruction. Okay. Now, the idea here really is, again, going back to the motivation, that modeling images is challenging. Yeah, if you look at the different places where inverse problems in imaging appear, it's very, it's super diverse. And so it makes a lot of sense to try to customize, to go away from saying images are piecewise constant, and to go to something where we can use examples of these images to formulate, to derive regularizers, to derive priors. Okay, so this really kind of introduced a step change. Yeah? So if you look a little bit closer at this example that I've just shown you, okay, here is the data, here is the TV reconstruction. What I always show at the bottom here is the quantification of how good this reconstruction is in comparison with the ground truth. This is all simulated, so we can do that. Where this is the PSNR, so the higher the better, and this is the structural similarity index, again, the higher the better, okay? And this is now a comparison, a learned approach, right, that I will talk about, by the way. This is the one I will talk about, yeah? And so if you compare this now with the ground truth, yeah, and you go again back to total variation, this is really, I mean, this really, I think we wouldn't have thought of, dreaming of being able to reconstruct images that look like this before deep learning came up. Okay, so there are various ways how people have thought of combining deep learning with inverse problem solutions. And here is a list that, I mean, I'm happy to share my slides, by the way, afterwards, because I'm not going to talk about all of these. I'm only going to focus on learning the regularizer. This is the setting I want to be in. But there are various ways how people have thought about combining deep learning with inverse problem solutions. And here you have a very, very small subset of references that should just give you some starting points if you want to look for things there, okay? But I will focus on learning the regularizer, and I'll give you a bit of a motivation why I want to do this, yeah? Which is here. So there's a lot of work that has been going into, this different types of approaches, deep learning for inverse problems. But there's still a lot of disadvantages, and those go back to my comment at the beginning that most of the work that is out there really lacks in mathematical scrutiny. So there are almost no theoretical underpinnings for deep learning approaches for inverse problems. There are a few exceptions, and there are more and more exceptions, which is good, so that the development is definitely going in the right direction. But just to say, just to emphasize how important this is, really, because these inverse problems are ill-posed. And so if you are not in a regime in which you are sure that your solutions can explain the data, are consistent with the data, are continuously dependent on changes in the data and things like this, if you lose this well-posedness, it kills you, because you have noise in the measurements that you need to take care of. Okay. This is, by the way, this just as a comment. There has been a lot of talk recently about instabilities, intrinsic kind of instabilities of deep neural networks for inverse problems. There are now also some very nice works which counter-fight this a little bit, which I'm very glad to see, because deep neural networks are not different to any other kind of total variation regularization or something like this. We just need to make sure that they're really regularizing the problem. And then you have the same issues as you have with other regularizers, okay? also a lot of times an interpretation of the reconstruction model is missing, yeah, or maybe only known asymptotically. Data consistency is in general not guaranteed, as I said before. And usually a lot of these approaches require lots of supervision. So sticking to the variational setting could resolve some shortcomings. And I'm going to show this now to you, in particular, provable notion of stability, of regularization, and data consistency of the solution. And in our case, also the supervision will be mitigated. Okay, so the framework we are in is, again, going back to our nice variational regularization approach. And what I want to do now is I want to use neural networks in a kind of plug and play fashion for the regularization term. I want to model the regularizer by a neural network. I want to learn it separately. I'll show you in a moment how I learn it. And then I want to plug it back in and in the end, solve my inverse problem with the variational regularization approach. Yeah, and so this is kind of summarized here. I don't want to learn how to reconstruct, which a lot of approaches do, but I want to learn the regularizer. I want to really have a very targeted way, a very targeted approach of how the neural network comes in. And the nice thing about this is that the mathematical guarantees, if you train this regularizer, if you model this regularizer as a neural network properly, the mathematical guarantees just come from the classical theory. So it's just, it basically comes for free. Yeah? Okay, and this is joint work. This, what we have been doing in this context is this, what we call learned adversarial regularizers. And this is joint work with several people. So we started this journey with my former PhD student, Sebastian Lunz. And then with Sebastian Lunz and Oza Nöktem from KTH. Now, I would say Shubho Mukherjee is kind of the main person behind the adversarial regularizer further development. And then this is also joined, so he is a postdoc with me, but he's joining Bath as a lecturer very soon, which is great. Then it's together also with Marcello Carioni, who is at the University of Twente, Søren Dittmer, who is a joint postdoc with Bremen and Cambridge, and Zach Shumyalov, who was a wonderful undergraduate student who worked with us over 2 summers. And yeah, so also this is what I'm going to show you is due to him. And here you just have a summary of the papers. Okay, let me just quickly check the time. Oh, okay, I'm doing it pretty well. Okay, so now what we want to do is we want, maybe I should ask, but I mean, I didn't explain yet anything about adversarial regularizers, but if people have any comments or questions about what I already said, maybe you want to make them now. I should maybe, how do I see the chat? Okay. So
maybe I think we're good in the room. Thank you.
You're good in the room. Perfect. Okay. So then I'll continue. Okay. So training regularizers adversarially. How do we do this? So we want now to make this regularizer in this variational approach data driven. So the main thing to think about is what is the loss function, right? What's the objective? The evaluation criterion for a good regularizer and a bad regularizer, right? And so this is basically this is what is on this picture is an explanation of how we train it. So in a way, when you think about it, what the regularizer should do is to distinguish between solutions to this inverse problem that I want to favor, that I want to see, and solutions to the inverse problem that I want to attenuate, right? So again, thinking about the total variation, right? What the total variation is doing, if you add it to a kind of least squares fit, let's think for simplicity just about denoising or something like this. It should attenuate the noise, right? It should attenuate oscillations, and it should preserve the edges in the image, okay? So in a way, how we train it is by exactly mimicking this, by exactly kind of training the regularizer to distinguish between kind of noisy reconstructions which show artifacts also coming from the inversion of the forward operator, and reconstructions which we like to see, reconstructions which have all the structures and the textures maybe and things like this that we want to see in our solutions. And so hence we start by creating images, examples of both of these scenarios. Okay, so we have a training set of what we call the good guys that are the ones for which, and we call them U star, that come from a distribution PU. And those should be the ones for which the regularizer is small. Okay. Now, what the good guys are depends on your application. Okay, so in CT, for instance, in computer tomography, our target is to solve a low dose, sparsely sampled in the angular direction, sparse angle CT reconstruction. Yeah? So hence our good guys could be, for instance, either coming from phantom data, for which I could increase the dose, or just take clinical data where the dose is also higher. Yeah. So take images that are in the more ideal scenario where I can get good reconstructions with standard approaches. Okay. So these are the good guys. And then the bad guys are basically the ones for which I want they should be the ones which the regularizer should attenuate. Okay. And those again depends on your application. What you choose is the bad guys, but the general principle is that the bad guys should be kind of baseline reconstructions. Those should be the reconstructions you want to improve upon. You want your deeply learned variational approach to improve upon. And so in CT, the most natural choice for those is to use filtered back projection, okay, the unregularized reconstruction. And this is modeled here, okay, so we start with, so we take as the bad guys images that come from this distribution Pn that we've created out of the data by applying, in general here, the pseudo-inverse of the operator, of the forward operator capital T, which in CT is the filtered back projection, okay? And then we train the regularizer in this kind of adversarial manner to be small for samples coming from PU, the distribution of the good guys, and large for samples from PM. In terms of equations, actually, this nicely boils down to the Wasserstein loss. The discriminator part so our inspiration was really Wasserstein GANs and taking out the discriminator from Wasserstein GANs for training the regularizer by this loss function here. Okay, so this is actually just in terms of a formula what I just said. So we are looking for a regularizer that is one Lipschitz. Okay, so this comes from the Wasserstein, the one Wasserstein definition. So we are looking for a one Lipschitz regularizer that if I feed the regularizer with samples from the bad guys, right, these are the noisy guys, the PNs, the regularizer should be large. I'm maximizing here. And if I feed the regularizer with samples from the good guys, the regularizer should be small. Okay. Now, a few comments. So first of all, the nice thing about this goes back to mitigating something about the supervision. The nice thing about this, how we train the regularizer, how we evaluate the regularizer, is that we do not need the good guys and the bad guys to be paired. And this is super cool for inverse problems when we really want to solve real inverse problems. And Emma just said that I really love to work interdisciplinary, so this is important for me. That we can work with real measurements, and we can use those to create the bad guys. But then we can, you know, if we have a way to create the good guys, it doesn't need to be connected to the bad guys, but if we have a way to create the good guys that show some of the structures that we want to see in the solution of this real inverse problem, then I'm okay, I can do that, okay? So this is nice. Now, of course, we are not searching for the regularizer over all one Lipschitz functions, and this is where neural networks come in. Yeah, so now we approximate this regularizers R. We parameterize them by neural networks. And in particular, what we do is we model the regularizer that we eventually put back into the variational problem as a sum between a little L2 squared fit. This is important later. I put this there to get existence, okay, because this makes my variational problem coercive. Plus, and you can choose this very small, so the effect is actually, it's almost no effect, just that we get well opposedness. And then the other term is now the neural network that I train with this criterion, where the neural network, where we tried two scenarios. So we just used initially with Sebastian also just an off-the-shelf convolutional neural network for that, which of course then means that eventually the variational problem that you solve is non-convex. Well, which is okay, but you know, mostly in variational regularization, we have been looking for convex regularizers. And so what we did with Shubo in particular is that we looked for convex parameterizations of neural networks. And we found this very nice parameterization that is in this paper here of input convex neural networks, okay? I think I have a slide at the end in my appendix if someone wants to ask a question about this, because I will not have time to explain how to really make those, well, how this parameterization looks like. But the nice thing is that you can do it such that it's input convex, so that it's really convex in U, okay, which is what we need. Right, and once we've done this, we also take this one Lipschitz constraint here and put it here as a penalty term, okay? And this is now eventually the loss function, the learning problem that I'm solving. Now, I think I will need to jump over this. You can show some things about, you can ask yourself, is this a good choice actually to train a regularizer like this? And in a way, you can get some evidence and justification that it is. In particular, what you can show actually, again, relatively easily, is that if you start, basically what this says, without looking at the equations, what this says is if you start with a noisy reconstruction and you do one gradient step in the direction of your, if you do one step in the direction of the gradient of your regularizers, you do one gradient step for the regularized problem, then you're going closer, and you're getting closer to the distribution of the good guys in the fastest way in the Wasserstein distance. Okay, so this is basically what this says. So in a way, it makes sense, right? So the regularizer points you in the right direction. Another nice thing is that under some quite typical assumptions that people also in GANs are using to show something about their generative models. What you can show is, and I can get back to these assumptions if you want to know more details later, but I just don't want to lose too much time. What you can show is that if you solve the learning problem perfectly, yeah, so meaning that you really optimize this Wasserstein loss, then a maximizer of this Wasserstein loss, which is, you know, a regularizer, is actually the projection onto, well, more or less the good guys. Okay, so this is also kind of a nice way to think about it. Yeah. All right, and this is just a summary, and then I show you some results. So the summary, just as a recipe almost, is if you want to do this, if you want to train a regularizer like this, you create the training data, the good guys and the bad guys. You train the regularizer with this loss function. Either you use a convex, this input convex neural networks, or just an off-the-shelf CNN, or anything. Maybe you have better ideas as well. And then you take the learned regularizer and you plug it back into a variational problem, which you solve with, I mean, we just used subgradient descent, we didn't put so much effort into this. Yeah? Okay, and the nice thing now about this is that we really get the well-posedness for free. Yeah. So this is for the non-convex version, and this is for the convex version. For the convex version, we get more, yeah, because we have convexity. So we get, and actually we have strong convexity even because we have this little L2 squared term. So we get even uniqueness, we get existence. We get also what is very nice is we get that this is actually a proper convergent regularization. This is also something that people in inverse problems really like to know about the regularization, which is, if you have your variational regularization approach, you have your data. If you let the noise level in your measurements go to 0, and you let your regularization parameter at a rate dependent on how fast your noise level goes to 0, at a rate dependent on that also go to 0, then what you want to show is that you're converging to the kind of ground truth solution, what is also called the R minimizing solution. Yeah, so to a solution that fulfills the inverse problem exactly, and at the same time minimizes the regularizer. Okay. So this is very nice. We could only show this in the convex setting. Yeah, although if we tweak the non-convex setting, you can also show something similar, but we didn't go there. Okay. Last comment is this is something we did with Marcello as a kind of extension. In what I showed you at the moment, the bad guys are fixed, right? I just have one baseline reconstruction that I use for this training set of the bad guys. Now, if you go back to this idea of generative adversarial networks, you could also think about using a generator to make the bad guys better and to challenge the discriminator, the regularizer, more and more and more. Okay, and this is basically what we did here with Marcello and Shubo. Okay. Again, more details maybe in another talk. Okay. Now, examples. I'll show you examples for computed tomography. This is the application we mostly looked at, although we also did others like deblurring and denoising. And Shubona is also doing some MRI examples. It doesn't matter actually, but this is just what we. Okay, this was, by the way, the timer, so I should wrap up. So this was what we focused on. And I'll show you two examples. So this is a sparse view CT where, okay, I'm adding noise to the measurements. This is all simulated. And these are abdominal scans from the Mayo Clinic OpenCT dataset that maybe some of you know. And then we are undersampling in the angular direction. And the reconstructions I'm showing you are filtered back projection. This is the baseline. These will be the bad guys, right? Total variation regularization, the adversarial regularizer, but already with this improved opponent, okay, that I just was referring to, the adversarial convex regularizer, and then learned primal dual, which is a kind of state-of-the-art deep learning approach that is supervised and that counts towards these learned iterative reconstructions. Okay, so just think about it if you don't know about learned iterative reconstructions, just think about it as a baseline supervised deep learning approach for inverse problems. Yeah, okay. Okay, so sparse FuST. So this is, I always show the ground truth on the left, and here is the reconstruction, filtered back projection. And again, this is just the quantification. So you can watch the numbers as well if you want. This is total variation. Okay. This is what you get with the adversarial convex regularizer. This is what you get with the adversarial regularizer, with the one that it was also improved with the updated bad guys. And this is what you get with learned primal dual. So maybe in this context, the winners are maybe those last two. And maybe something to say here is, again, you know, we are not that far off from the state-of-the-art deep learning reconstruction, but we have theoretical guarantees, and this works in an unpaired setting. So this is as a comment. The next example, and then I'll finish, is limited view geometry, where we do CT, but we do CT where we have a whole range of angles totally missing, which means I don't see the object from one direction, right? Or from a range of viewpoints. I don't see it from a continuous range of viewpoints. And this is kind of visualized here by this toy example, where if you look at the measurements, a whole gap, there's a whole continuous gap in these measurements. And when you reconstruct now with TV in this case from these measurements, you see that the object isn't visible, therefore, from these directions. And again, I have the same methods that I'm comparing against. Oops, did I? Yeah. Okay, so this is limited angle. Again, Mayo Clinic CT Open data set, ground truth, filtered back projection. You can really see very clearly where the missing angles are. This is what you get with TV. This is what you get with the adversarial convex regularizer. This is what you get with the adversarial regularizer, with the non-convex one, which is super strange, right? Maybe the important thing here to say is, so we can only suspect what is happening here. Yeah. So somehow, if you think about what the adversarial regularizer is trying to do, it's trying to differentiate between, let's go back here, between these guys, the good guys and the bad guys. And somehow what seems to be the case is that the adversarial regularizer in the non-convex setting, where it's super flexible and everything, is trying to compensate for the artifacts that we get from the limited view, that are these line artifacts here that you see, where you don't see the object. Yeah? You get these line artifacts. And somehow it tries to overcompensate by introducing lines kind of that are going in the other, you know, to kind of reconstruct instead of the lines, to kind of reconstruct what the ground truth, what the good guys should look like. Something like this. It seems that these have an influence. So this has somehow learned the wrong thing. But the important thing is, it's a valid regularizer in that the reconstruction is consistent with the data, as is also this reconstruction, right? So they are both consistent with the data. It's just that this is not a very good prior that has been learned here. Now, learned iterative reconstruction, this learned primal dual, state-of-the-art kind of supervised reconstruction, is really messing it up here. And I think this is very important now to really emphasize the importance of mathematical guarantees, because if you look, so it looks great, right? If you just look quickly, it looks great, but the closer you look, the more worried you become if you compare it with the ground truth. The whole shape is kind of made up, right? Doesn't correspond to the shape of this body. If you look at the bone structures here, they're totally different to the actual bone structures here. Here, if you look at the vacuum bits here, so this is again very different. So this is not something we want, right? And I think it's very important to emphasize that deep learning cannot do magic. If it does magic, then something is wrong, right? Because the measurements are the measurements. You can't get more out of the measurements as the measurements give you, right? Well, the prior assumption can help you, but still, you know, you need to fit the measurement. You need to be able to explain the measurements, which this reconstruction doesn't. Which this reconstruction doesn't do. So we have some extensions. I'll skip that, and I'll finish with some takeaway messages. So I think deep learning we've really seen lots of success stories with deep learning and inverse problems, and I've just shown you one where we worked on these adversarial regularizers. They're really nice. I mean, I just like them a lot. I'm biased, of course, but I like them a lot because they really fit deep learning into a rigorous mathematical framework. And of course, there are many open questions. The convex regularizers, I think, have a lot of more potential. At the moment, they're limited by our ability to parameterize these convex networks in a kind of richer way. It would be nice to learn, to know more about qualitative properties of the regularizers and so on and so forth. But I think the biggest problem, and this is a call to the whole community, I think, is inverse problems usually appear in applications where we are not interested in visually pleasing images. Okay, so I showed you PSNR and SSIM, but in a way, in the applications that inverse problems appear, they're kind of not completely meaningless, but they're kind of secondary. Okay, what we really need to work on is to make these approaches targeted to what we want to do with the images eventually. Yeah, so to make a clinical decision, to make a diagnosis, a prognosis, develop a treatment plan, for instance, in the medical context. And also really work on scenarios where they pay off, where they make these decisions easier, where they make these decisions maybe possible for the first time. For instance, bedtime screening of patients, bedside imaging of patients and things like this. Yeah, where really the measurements will be super bad. This is where I think this can have an impact. So thank you very much for your attention.
Thank you, Carola. That was awesome. I feel like I really learned a lot. And I know there's several folks in this room who work on problems like this. So I'm going to let one of them maybe come up with a question, or if somebody wants to pop it into the chat. Oh, come on up.
Do I use this one?
I think either works.
All right. Thanks for the presentation, Carol. I have a question. In your regularization term that you learned, that based on adversarial learning, essentially what it tries to do is to give the a good score for a clean image and a low score, I mean high regularization value for anything bad, right?
Yeah.
Do you think the issue that you observe is because you pick only a subset of bad images, meaning filter back projection results as a way to train your regularizer, because you really don't show it all kinds of other diverse types of bad images, what you call bad guys, in your training set, right? How much do you think that influences its performance rather than anything else?
Yeah, I think so I think I agree, because these I think these artifacts really come from the filtered back projection artifacts somehow. So actually, this is a really good comment. We haven't investigated that. In this context of limited angle, I think it would be good, because this generative approach where you make the bad guys better could actually, this is a really good idea. Thanks a lot for suggesting it. Yeah, I think that could help.
Thank you.
Thanks.
Hi, yeah, thank you very much for the very nice talk. This is Katie Bauman. I had a similar question as Beck, but I was just also wondering, did you try to use your learned regularizer and then see how it would score on images that were different than like the CT images that you've used? Like, I don't know, images even from MRI, or ones that were from like, or just cats or dogs, or just pure noise. How would it do in those kind of situations? And maybe it connects more to Beck's question as well.
Yeah, so thank you for the question, Katie, because so I only have empirical answer for that. Yeah, so we did experiments, and in particular, Sebastian did experiments in his PhD thesis where he did cross dataset experiments. So he, for instance, trained on knees and applied it to abdominal scans, and the other way, or this is not abdominal, for lung, right? So he trained on knees and then applied to lung, and the other way around. And he also did experiments where he also changed the noise level. So he trained, let's say, on low noise, and then he applied it to high noise, and also the other way around. And most of the time, this works well. It doesn't work as well as if you would train exactly on the, you know, on the thing you want to reconstruct. And this is maybe kind of logical, but it is not, the decrease in performance is not bad. What is not a good idea is, from his experiments, if you train, and again, this makes maybe conceptually sense, if you train on low noise measurements and you apply to high noise, this doesn't really work, because in a way, high noise really gives you different artifacts and so on in your reconstructions that the regularizer, when it was trained, hasn't seen. So yes, we did some tests. Thanks for the question.
Thank you.
Thanks.
Hi, thanks for the talk. I just had a question. So could you clarify, like, how is this an improvement on, say, like if I just trained a GAN on the data set of the good images of the good guys, like a regular typical GAN where you just want to generate good images, and you take the adversary there, the discriminator there.
So which is
So
maybe
like
what we did here, right? I
Well,
mean,
here you-
so in a way, you can choose whether you choose a generative model to produce your solutions to the inverse problem, or you instead parameterize your regularizer as a neural network and then put this regularizer back in the variational approach. So again, I think this maybe goes back to my very first statement here, which is that we do not want to learn how to reconstruct. We really want to just learn this regularizer and then reconstruct with a variational model.
Oh, I mean, like, what if that regularizer is a GAN where you don't have, I mean, maybe that's what you showed. I don't see it, but.
You mean just train it on the good guys, but not the bad guys?
Yeah.
Oh, no, I know what you mean. Yeah, okay. So the issue with this is that here, the candidates that you get when you kind of also iteratively solve this, definitely you will see some bad guys. Right. So just think about gradient descent or something like this. The first, and let's say you just start by as an initial step, you start with your baseline reconstruction, which is a kind of least squares fit maybe, or filtered back projection or something like this. It will not have seen these type of artifacts that are coming from the forward operator. Introducing the bad guys is a way to influence, to already show the regularized kind of artifacts that are coming from the forward operator, right? Because we create them by this pseudo inverse applied to the measurements.
So like, because the bad guys, the adversary would never have seen them in training, it just wouldn't really output any meaningful signal, is what you're saying?
That's what I think, but
okay.
Yeah.
Thanks.
You're welcome.
Hi, thank you very much for the great talk. I just have a question about your takeaway message. I really agree with that. But I just have a question about, like, if you think about, like, if you want to go beyond like image reconstruction to some more like downstream tasks, there are some challenges with it, because sometimes you don't have a nice function to evaluate the performance. You might need to train a segmentation network or classification network. Sometimes you need to do it like human in the loop. Could you share some wisdom about like how to develop theoretically guaranteed algorithms in that case where you have those challenges? Thank you.
Thanks for the question. So what we did before in the context of learned iterative reconstruction was to link the learned iterative reconstruction training with, for instance, as you just mentioned, the segmentation network. And then to combine the loss functions for the segmentation and the reconstruction with an appropriate weight. And the interesting thing is, you really need both losses in your loss function to influence, to have a reconstruction that gives you the best segmentation, but but yeah, so you can do this. The problem is, of course, is it becoming more challenging because you have many more parameters and so on. Your problem becomes much larger. We haven't done it in the variational regularization context yet, but you could imagine that you do this, right? By training, by just training alongside the, training the regularizer, training alongside also a segmentation that takes the output of the variational model and then segments it, something like this. Or actually, maybe even a better idea is to combine it with this. Sorry, I don't want to confuse things too much. Where was it? To combine it with this idea of having a generator and a regularizer and then training the segmentation alongside the generator. So I think it's possible. I think it's a very good comment, but we haven't done it in the variation context yet. We have a paper on task adapted reconstruction where we do it for learned iterative reconstruction. There we did it for segmentation and classification. And yeah, it works. It's just computationally challenging.
I see. Thank you very much for your answer.
Thank you.
All right, I know there are still some more questions in the room, but maybe you can follow up offline because we've got 10 minutes for everybody to grab a coffee so we don't have a revolution on our hands. But let's thank our speaker again.
Thank
Really
you.
interesting
Thanks
talk.
a lot.
Thank you, Carola.
Thank you.
Right.
Thanks, Emma.
Everyone who's joining remote, go make yourself a cup of coffee.
This meeting is being recorded.
Can you hear me now?
Yeah, I can hear you.
Okay, so I guess it's okay.
Okay.
This meeting is being recorded.
We're all ready to go here, so you can get us started back up.
Okay, great. Can you hear me?
Okay, yeah. Can you hear me now? Okay. So, hey everyone, welcome back from the break. It's my great pleasure to introduce our next keynote speaker, Dr. Payman Milanfa. Payman is a well-known pioneer in computational imaging society. He is a principal scientist and director at Google Research, where he leads the computational imaging team. Prior to this, he was a professor of electrical engineering at UC Santa Cruz from 1999 to 2014. He was associate dean for research at the School of Engineering from 2010 to 2012. From 2012 to 2014, he was on leave at Google X, where he helped develop the imaging pipeline for Google Glass. Most recently, Payman's team at Google developed the digital zoom pipeline for the Pixel phones, which includes the multi-frame super resolution pipeline and the Razer upscaling algorithm. Payman received his undergrad education in electrical engineering and mathematics from UC Berkeley, and the master and the PhD degree in electrical engineering from MIT. He holds 20 patents. He also founded Motion DSP, which was acquired by Cubic Incorporation. Payman has been keynote speaker at numerous technical conferences, including Picture Coding Symposium, SIME Imaging Sciences, SPAE, and the International Conference on Multimedia. Along with his students, he has won several Best Paper awards from the IEEE Signal Processing Society, including the 2021 Best Paper Award for kernel regression in image processing and reconstruction. He is a distinguished lecturer of the IEEE Signal Processing Society and a fellow of the IEEE for contribution to inverse problems and super resolution imaging. Payman is talk about his thought on denoising today. So let's welcome Payman.
Thank you very much. I'm very pleased to be with you, hopefully next time in person. So let me go ahead and get started in the interest of time. So today I'm going to give an overview of denoising as a building block for several things: imaging, inverse problems, and machine learning. So let's go ahead and dive right into it. So imaging, as you all know, is the very simplest of inverse problems. You measure a signal that's been corrupted by noise, and you want to design some sort of filter that will take the noisy image and produce a clean version of it. The history is really quite rich. There have been many contributions over the years. I'm not going to go through every single one of them in detail, but it's suffice it to say that there have been thousands of publications in this area. In fact, so much so that in 2010, one of my students and I noticed that many of the papers were kind of producing very similar performance, and we decided to work on this problem of trying to see if we were getting close to the performance bounds, sort of the statistical performance bounds in the mean squared error sense. And we wrote a paper with the provocative title of "Is Denoising Dead?" And as you might know, the title of any article that starts with a question, the answer is likely no. And this was the case here as well. And the next decade followed with many additional contributions, mainly in the direction of learning-based methods, leading up to today. So I would say, as of right now, there are, there's very little room for improving the quality of denoising with standard Gaussian noise anyway, but many new use cases of denoising have been developed. So just to give you one example of many, we recently worked with some colleagues in Germany and Italy, Mangal Prakash and Florian Jog, to develop an unsupervised approach for scientific applications. This is denoising of very noisy microscopy images. And this is a hierarchical approach that is able to not only get rid of noise, but also preserve very fine detailed structures, as you can see here. We presented this in ICLR. This is just one example of the set of things that we can do. Okay, but denoisers can do much more than just getting rid of noise, and that's the whole point of this talk, really. And what we want to talk about here is solving more general inverse problems, and how denoising can form the basis of many types of neural networks, as you're all familiar with. So here's kind of an unexpected result. The image on the left is a blurry input, and the image on the right, it has been reconstructed. And the remarkable thing here is that the engine for reconstructing the image on the right is the median filter. And on the surface of it, if I told you I can use a median filter to deblur, you would think I'm a little bit crazy, but this is in fact the case. Nowadays, we can do these things. Okay, so let me set up a very general idea here. What are denoisers? So I'm thinking of denoisers as a function f that takes 0, 1 crossed with itself n times, and that's n pixels to itself. And the vector x here is the image ordered in a column vector. Typically, but not always, I should say at least ideally, these operators are non-expansive. So basically they behave, if you want to think about it in terms of linear filters, they behave sort of like nonlinear versions of low-pass filters, low-pass operators. So before I start getting into anything more fancy, let me start with a very simple idea, a very natural decomposition that you can use denoisers for, that gives rise to kind of perfect reconstruction, multi-scale decomposition. So here's the idea, very, very straightforward. So let's say you use the denoiser, and then you decompose the signal x. This is kind of a splitting of the identity operator. So you apply the filter f to x, and then you consider x as a decomposition of the filtered image plus the residual. And so the residual here is on the right-hand side, obviously. So we call f of x the smooth version of x, and then x minus f of x, we call that the Laplacian, or the residual. All right, now we can take f of x and repeat the process, do exactly the same thing. So you apply f to f of x again, and then you like the residual of that. And the last term remains what it was, of course. And you can just repeat this process. And it turns out that this works very well in terms of a nice decomposition that gives you exactly x back. And it's useful when f of x is non-expansive in practical settings. In fact, you can take the denoiser and you can think of it as parameterized by some set of parameters alpha. And these could be weights. If f of x is a CNN, it could be the weights of the CNN. It could be the denoising strength, something related to the variance of the noise, etc. And you can repeat this process, as I said. So here's what happens. You write x as f applied n times, and then an accumulation of residuals here on the right-hand side. And these residuals are just the difference between applying fk plus 1 times and applying fk times. So now that you have this decomposition, you can think about this will reconstruct x exactly. But what if you didn't want to reconstruct x exactly and you wanted to reconstruct some modified version of x? Well, you can take this equation here on top and put some coefficients in front of it and recompose it. So the top one is decomposition, and the bottom one is recomposition. And now you have some set of free parameters to play with. And you can think of the alpha, which were the parameters of the denoiser itself, and you can think of the beta as sort of control knobs. And now you can generate an entire family of processed images based on X and a core denoising filter. And now let's say you have examples. You have input and output examples. Let's say, for example, you take Photoshop and you go into Photoshop and you take an image xi and you put it into Photoshop, you perform some complex operation and you get xi hat. And now you have paired examples. Now you can use these paired examples with a setup like this. The first term here is the training error, where you try to see if you can generate the xi hat by some combination of applying the filter n times and the residuals, that recomposition that I showed you earlier. And then you can search over the parameters alpha and beta, optimize over alpha and beta, while regularizing alpha and beta as well. So this framework, really simple, from a splitting of the operator, identity operator, you can get a very rich set of filters. So here's an example. You can start with an input image. You do this decomposition. You can apply nonlinearities to the output as well, and you blend them back together and you can get the output. And the reason this works is because basically you have a multi-scale decomposition that's simply based on the action of the denoiser. You can do many, many different things with this setup. You can start with an input image that doesn't really have noise. This image was taken by a professional photographer, Andre Dragan. It's a very clean image, but there's a lot of texture in it, as you can see in the man's face. So we can use this setup to basically reduce the high frequency stuff and do wrinkle reducing. We can cartoonize and many other things. We can do dehazing, go from A to B, as you can see here. So this should give you a sense of these kinds of filters. As I mentioned, these are effectively a sort of residual network, if you like, in a very, very simple setting. All right, so now let's move on and talk about the general set of nonlinear denoisers. So I'm going to talk about 3 general classes of nonlinear denoisers, and they're very much related to each other. The first I'm going to call pseudolinear denoisers, and these are they include non-local means, bilateral, BM3D, et cetera, Bayesian denoisers like maximum a posteriori and minimum mean squared error. And then other types of denoisers, which are PDE based or CNN based. And it turns out these are also related to the other categories, as hopefully I'll have a little bit of time to explain. So pseudolinear denoisers first. So think about linear denoisers first. How do they work? You take the input pixels, some group of input pixels, and you combine them with some weights, Wij, to get one of the output pixels. Now, the only thing that distinguishes pseudolinear denoisers from linear denoisers is that these weights that you use might be possibly data dependent. And that turns out to capture a very wide variety of filters that we use in practice. Let me, for convenience, write this in matrix form so that I don't have to carry all the indices around. So here I'm writing one of the output pixels in terms of all the input pixels. Now, the filters typically don't involve all the input pixels, so some of these weights might be 0. But regardless, I'm going to write all the weights that point to one of the output pixels into a vector. And then I'm going to stack these vectors into the rows of this matrix W. And if I do that, then the pseudo-linear filter becomes this function f of x is W times x, but W is a function of x, and W is an n by n matrix. What are these weights going to look like? Well, so for instance, in the case of the non-local means, the weights might be differences between the values of the pixel or patches at various points in the image. So here's an example of if you take a little neighborhood around this blue pixel and compare it to all the other neighborhoods in the image, you might get a weight function that looks like this. So the weights W are effectively a normalized version of these kernels Kij. The reason these are useful and interesting to look at is twofold. One is that these pseudolinear denoisers tend to be approximate or empirical Bayes denoisers, and this has been illustrated in several papers over the years. And the second reason is that they're very convenient in terms of implementation, because they are distinctly 2 stages. One is a nonlinear stage of weight calculation, and the second stage is just a linear filter that you can apply. And so this weight calculation can almost be done independently of the next stage, and this makes them very, very interesting in terms of optimization and making them faster and so on. All right, so now going on to MAP versus MMSE, I think this is just a quick cartoon illustration. MAP is the argmax of the posterior, and then the MMSE is the expected value of the posterior. These 2 things won't coincide with each other unless the distribution of this posterior is perfectly symmetric and unimodal. All right, but let's get into the specifics of the MAP and MMSE denoiser a little bit more. So the MAP denoiser has this particular formulation here. So this first term, the L2 norm that you see here, comes from the assumption of the Gaussian noise. And the second term here is typically what we think of as a regularizer, this phi of u. Another way to think about this from an optimization language point of view is that this is also known as a proximal operator. And it has many, many really useful and interesting properties. In the context of stochastic inverse problems, this phi of u, which is the regularizer, also is known as the negative log of the prior distribution on u as well. So if you go through the math and look at some of the literature, another way to write this optimization on the right-hand side in a kind of closed form is that the map estimate is x minus sigma squared, this is the variance of the noise, times the gradient of this phi sub sigma. Now, phi isn't exactly this phi that you saw up here, but it is a smoothed version of phi. And it turns out the smoothed version has a name. It's called the Moreau envelope. Let me show you an example. So if you pick phi to be the one norm, this phi that we're talking about here, if you pick that to be the one norm, that's this blue curve. The phi sigma, which is the smoothed version of it, is this red curve that you see here. It behaves like L2 down here and behaves like L1 up here. That's the Moreau envelope. And then if you look at the gradient of this, you get exactly what is known as the soft thresholding operator, which is the green curve that I've drawn here. Now, what about MMSE denoisers for the same case? I'll describe it for the same example. So there's a very remarkable formula for MMSE denoising that deserves a lot of attention. And I feel like it's not as well known as it should be. So if you look at this integral on the right-hand side, you get the sense that you would need P of u, right, in order to compute this integral. But it turns out that there's this beautiful formula by Tweedy. It was communicated in a personal correspondence to Robbins, and then it was rediscovered in multiple different instances. What it says is that the MMSE estimate can be computed as x plus sigma squared gradient of P of x divided by P of x. Now note that this marginal density of x, P of x, doesn't directly involve u anymore. In other words, this is just the distribution of the noisy image that you get. So what this indicates on the right-hand side is that if you just have the noisy image, the empirical distribution, if you were to estimate this P of x, if you were to estimate this right-hand side, you should be able to build the MMSE denoiser at least approximately. That's a remarkable fact that allows the MMSE to be approximated using many of the different approaches. And so many of those pseudo-linear denoisers that you saw earlier are based on approximating this right-hand side given just the noisy image. So let me rewrite this a little bit to make it look like the previous map denoiser. So if I just massage this a little bit, I write this ratio as the log of P of x, gradient of the log of P of x. And then I think of, I just rename negative log of P of x as this phi sigma with a tilde on top of it to distinguish it from the last phi sigma that I showed you. What you have is a very, very similar formula to what I showed you earlier. Again, x minus sigma squared gradient of some smoothed version of phi of x. And this smooth version is simply, in this case, is just a blurred version of the prior. And the blur is determined by this Gaussian, whose width is dependent on the variance of the noise. And so here's the example that corresponds to that. Again, I start with a one norm as the regularizer. And the red curve here is the Bayes posterior loss, which is a differently smooth version of the L1. And then the green is the smooth thresholding instead of the soft thresholding that I'm calling. All right, so let me quickly recap what I just said. The pseudo-linear denoisers have this form W of x times x. Just for convenience, I'm also going to write this as x minus L of x times x, where L of x is a so-called Laplacian action on x. It's just identity minus W. Map I can write as x minus sigma squared gradient of the Moreau smooth loss, and the MMSE I can write as x minus sigma squared gradient of the log, negative log of the blurred prior. So what you see here is a similarity in the form of these functions. So the general form is that it's x minus something, and this something turns out to be the gradient of some function. So in all of these cases, what you can see is that the denoiser behaves like a perturbation. It should behave like a perturbation of identity, because if you think about it, if the noise is very small or vanishingly small, going towards 0, the operator ought to act like an identity operator, right? So if the noise is not present at all, then the denoiser ought to just give you the image back. So that's the ideal behavior. It behaves like a shrinkage, right? It's basically taking X and taking something away from it. And you can also think of it as a gradient step on possibly some energy function. Here it's pretty clear what that energy function is. And the gradient step is going to be proportional to how much noise you have. All right, so let me build on this a little bit more by mentioning that having that observation, you can actually build the denoisers from energy functions somewhat more directly as well. And this nice paper by one of our colleagues, Regev and others have explored this idea. So if you think about the general form as x minus v of x, you can think of v of x as being defined as the gradient of some energy function. This energy function could be something that's in fact trainable. And in that case, then this formulation that I just described up here can be written as the gradient of 1/2 norm x squared minus e of x. Okay, and this is just an algebraic manipulation. So if you apply this gradient to the inside of this bracket, you get exactly this thing on top back. So E bar is basically this difference between the L2 and E. And if E is convex, then this is the difference of two convex functions. And as you know, there's a lot of nice optimization algorithms for dealing with this type of function as well. The useful side effect of this particular formulation is that because v of x is the gradient of this energy, a gradient of a scalar field function, it is by definition a conservative vector field. And in fact, the gradient of f is symmetric as well. And that turns out to be technically important for proving things about the convergence and stability of some of these algorithms. And of course, this is true for MAP and MMSE as well, because the E, I gave you a very explicit formula in terms of the smooth version of phi in those cases as well. All right, so this is related to a number of things you've seen in the machine learning community, where they've used a technique called score matching. And it turns out the denoising residual is exactly what gives you this idea of score matching. And so let me explain for a moment exactly how this works. So think about this f of x as x minus the gradient of some energy function, as I just said. Now, if you remember, I can write this for the MMSE case as x plus sigma squared gradient of the log of p of x. And I can rewrite it as x minus sigma squared times the gradient of the smoothed version. But I can also turn this equation around and think about the gradient of E as x minus f of x. So remember, x minus f of x is simply the residual of the denoiser at x. And so what you look at here is that the local geometry of the manifold of images near x is measured. If E is a proper representation of a surface of a manifold that describes the behavior of images x, then the gradient of that surface is in fact the image residual. And so geometrically, if you like, what this tells you is that good denoisers learn the local geometry of the image manifold. And in fact, a good denoiser, sort of the empirical theorem here would be that a good denoiser can allow us to sample from and project onto this manifold. And this observation has been used in many, many different papers, some of which I've listed here, some of the earliest ones, in order to build machine learning algorithms. So one of the most impressive and popular methods that has been invented recently was, it's been developed recently. I guess it's been around for some time, this idea of denoising diffusion. Exactly uses this idea to project onto the manifold of images. The forward diffusion process is as follows. You start with an image and you slowly add little bits of noise to it. And remember what this does is that, let's say X comes from some distribution, right? So if this image, if you do this on the distribution of all images, what you're doing here is at each stage, by adding a little bit of noise, what you're doing is you're convolving the distribution of the x's with a Gaussian. And so what you're doing is you're just blurring the distribution closer and closer to a Gaussian. So when you have enough noise, you basically have a Gaussian distribution at the end. And so the idea of the diffusion, denoising diffusion models is to reverse this process. And it turns out this is doable. And there's an explicit, under certain conditions, there's an explicit inverse for this. And that involves the so-called score function. This is the gradient on x of the log of the p of x. And this is basically the same function that I showed you earlier. And if you recall, we talked about how the score function can be approximated or interpreted as the residual of the denoiser. So you can see how the residual plays a role in kind of taking this function backwards. And this work has, of course, been the engine that has brought a lot of the image synthesis technology past the age of GANs, right? Kind of this diffusion models beat GANs on image synthesis was a harbinger of many exciting things to come. Okay, I want to mention one of the pieces of work that we've done in this area, and this is using conditional denoising diffusion models. The idea here is that you're not trying to take an image that is all noise and kind of reverse the diffusion and get a sample image, but rather you're starting with an image that isn't, it's not just noise, it's just some imperfect version of an image that you like to perfect. In this case, we want to do deblurring. So it's conditional because you start with an image that actually bears a resemblance to what you want at the end. And what we've done here is to explicitly decouple a conditional diffusion model into two pieces. One is deterministic and the other one is stochastic. These two parts are then trained jointly and comprise a single stochastic deblurring model. So the idea here is that this initial predictor is basically deterministic. You can use any deblurring method that you like. If you use a better one, of course, that's great. But this doesn't get you all the way over there. So this blur here is fairly huge, and so it gets you part of the way there. And then we have this stochastic network that is driven by noise and these diffusion processes that predicts not the image, but the residual of the image. Okay. And then by combining these two together, you get a sample of the final result. And because this is a stochastic process up top here, you can get multiple instantiations of the sample. And then from those, you can construct various sorts of estimates. And this tends to outperform many of the existing methods. And the advantages that it has is that it produces a significant improvement in perceptual quality, and much more efficient sampling, and it gives you a very flexible perception distortion trade-off, as you can see in this curve here. So this paper is being presented, I should say, at CVPR right now, and it's in collaboration with our colleagues. Jay Wang was an intern in our team, and he's a PhD student of Alex Demakis at UT Austin. All right, so sort of the last piece of the puzzle that I want to describe here is the use of denoisers as regularizers or priors. So I've used denoisers as an engine for various different things so far, and in the community, in the imaging community, two major works were developed in this direction of directly using denoisers as priors or regularizers. The first one back in 2013 was the plug-and-play prior model for reconstruction by Venkatakrishnan, Bowman, and Wohlberg. And the idea here is to use an ADMM to minimize a regularized loss function. And then in one step of the ADMM, you replace what looks basically like a proximal operator with an arbitrary denoiser. And the other one, inspired by the first, was the regularization by denoising approach. So this, the plug-and-play approach originally did not, it didn't involve the optimization of a particular loss function, in the sense that once you took this ADMM and you replaced that one step with a with an arbitrary denoiser, you didn't have an interpretation as a strict loss function anymore. What we tried to do here, somewhat imperfectly, was to come up with kind of first principles, start with the Laplacian regularization, where this L is a Laplacian operator, possibly data dependent, and generalize it to arbitrary denoisers. This required us to make a bunch of assumptions. But if you look at either of these approaches, the most important thing to realize is that the process of reconstruction is as follows. You apply an iterative process where a linear operator acts on the image, and then denoiser, and then a linear operator, and then a denoiser. And this also bears a striking resemblance to the diffusion operators that you saw just in a couple of slides ago. So these are all sort of related to each other. All right, so for the Laplacian regularization that I just mentioned, that kind of what was the basis of kind of where we started, inspired by the plug and play approach, is so you start with this regularization X transpose LX, where L is an image-based Laplacian operator. This was studied for a number of years, all the way back to 2007, 2008. One of the difficulties with this is that constructing a Laplacian matrix is hard because its dimensions are very huge, and so the approximation is challenging and so on. It's hard to work with because it's also dependent on X, but you can, in an iterative setting, you can circumvent that by keeping W fixed per each gradient step, and then play various games with it. So what we thought was to go a little bit further. So if you remember, this L of X is I minus WX. So this term here, X transpose LX, you can also think about it as X transpose times I minus W times X. Okay, so that's this here. So we start with this, and then we say to ourselves, well, this WX is a very specific form of denoising. So why not just replace it with an arbitrary denoiser? And so that's what we tried to do. X transpose X minus F of X. And it turns out this is a very profitable thing to do under the right regularity conditions. Namely, the Jacobian symmetry. The denoiser has to have a symmetric Jacobian. It has to be homogeneous. And so in practice, some of these conditions are not satisfied. But somehow, magically, and some of this has been unpacked since then, even if these conditions are not satisfied, this approach seems to work. But again, it won't have a very strict interpretation as this being an energy function. In any event, under these conditions, it turns out that the residual is in fact the gradient of this R of X, if these conditions are satisfied. So this is very profitable, which means that if you're going to do this optimization with this X transpose X minus F of X as your regularizer, the gradient is rather easy to come around. All right, so again, let's say you want to solve a linear inverse problem for the time being. H is, let's say, some blur operator or something. So this first term is your data fidelity term, and the second term is your regularizer. And under these conditions that I mentioned, it's very easy to get access to the gradient. The first term, the gradient is trivial to compute. And the second term, as I said, the gradient is basically X minus F of X. If the first term is convex, and it turns out under the right conditions, the second term is also convex. And you can leverage the powerful optimization algorithms to minimize the overall cost functions. And as I said earlier, a bit of a mystery is that even when the assumptions don't hold, good denoisers tend to give good performance in other tasks as long as you stop the iterative process with some reasonable fidelity criteria. Okay, so let me give you one example of optimizing a loss function, this loss function with an iterative method, and this is a fixed point operation. Many other methods are, of course, possible and have been developed by many folks in the audience, I'm sure, as well. So if I were to write an explicit step of the fixed point iteration, what you see is that I can decompose it into two pieces. This first piece, H transpose H plus lambda I inverse, H transpose Y, is just fixed. It doesn't change in the iteration. You can think of this as a vector B. Okay, the second term here is a linear operator M. I've written out explicitly what it is, times F of X. And so if I were to write this all out in very simple language, and define zk as this f of x, I get this process where I apply a linear filter to z, I add a bias, and then I apply a denoiser, and that gives me the next iterate. So again, as I said before, this fairly simple looking operator emerges, or this pattern emerges. You apply an affine operator, you apply a denoiser, you apply an affine operator, you apply a denoiser, and this becomes the iteration. So let me just show you a few examples for deblurring. So this is the ground truth. This is the blurry version. This is regularization by denoising using the median. And these are a number of other algorithms that have competitive behavior or competitive performance. So I know I started a little bit late, but I want to keep us on schedule. So I'm going to try to kind of finish on time. And so let me conclude by saying that the denoisers are, I hope I've convinced you in whatever 17 minutes or so that denoisers are a fundamental building block. They form stable perturbations of identity. You can think of them that way. And they're very general. They can solve many problems. And some challenges remain. As I said, the behavior of denoisers gives you insight into the nature of images, but it's still, our understanding of that process is still rather imperfect. And I think that's a really interesting area of research to be continued. Okay, so I'm going to stop there and leave some room for questions. Thank you very much.
Oh, thank you very much, Payman. So very inspiring talk. So, any question from the room and the Zoom?
We've got one over here.
Thank you for a very interesting talk, Payman. I have one question. In fact, it relates to your original formulation of red with an explicit loss function. And it also relates to the it has potential papers that you shared and plug and play paper. One topic that kind of comes up over and over is, do we lose anything by having an explicit loss function versus not having it a la plug and play? So from your experience, is there anything restricting in being able to have an explicit loss function?
Yeah, it's a very good point. I don't think so necessarily. I mean, I think in some ways our own training has brought us to this point where we look for optimizing some explicit loss function, but I don't think that's really necessary. There's plenty of algorithms that work really well without an explicit loss function. I mean, you have these equilibrium methods that work really well. You have other kinds of empirical ways of setting up problems that work pretty well. I think it's nice in terms of having an interpretation and having some nice mathematics around it and some nice optimization around it, but I don't think it's explicitly necessary to have a clean loss function.
Thank you.
So any other questions? Well, actually, I want to take the privilege to ask one question. So I think so. So since Payman, you mentioned that the denoiser can be used as the general prior for the inverse problem, but I'm guessing maybe for some, denoising and deblurring, there's still some quasi-linear or quasi-linear problem. So for the highly nonlinear and non-convex problem, maybe there are some special difficulty, I'm guessing. So do you have any comments or suggestions for people who want to use the RAD or plug and play for some highly non-convex nonlinear inverse problem?
Yeah, I mean, I don't know if I have any general like broad set of wisdoms to come to impart here, but I think if you think of denoisers as somehow just giving you information about the class of images that you're looking at, that is a very general and useful guideline. Now, I'll say this. If you're looking at the class of natural images and you've developed a denoiser that does really well on natural images, then that's an appropriate match, right? but one has to think about whether a denoiser that's developed for natural images would work well in the context of, let's say, MRI reconstruction. Right? So it may be that a different class of denoisers gives you better insight or a better implicit model of the images in that particular class of problems that you're trying to solve. So I wouldn't say it's necessarily the algebraic structure of the problem. It's more the geometric structure of the class of images that you're trying to reconstruct that might direct you towards one class of denoisers versus another.
Okay, thanks.
Yeah.
Okay, let's check the payment again. Yeah, very inspiring talk. Okay, so let's move to our next speaker, Christina Monacoa. So Christina just finished her PhD in electrical engineering and computer science from UC Berkeley, where she's a member of Laura Waller's computational imaging research group, and she will be starting her postdoc at MIT this fall through the support of MIT postdoc fellowship for engineering excellence. Her research focus on making more capable cameras and microscopes through the co-design of imaging systems and algorithms. Her research lies at the intersection of signal processing, machine learning, and optics. Christina received her bachelor's degree in electrical engineering from State University of New York at Buffalo. She's a recipient of the NSF Graduate Research Fellowship and the NDSEG Fellowship. Outside of research, Christina has a strong record of service and mentorship through leadership roles in electrical engineering graduate student association, as well as women in computer science and engineering at UC Berkeley. Let's welcome Christina.
Thanks for the intro. Let me go ahead and share my screen. All right, I'm really excited to be here with you today virtually to talk about some of my work on physics-informed machine learning for lensless computational cameras. So in computational imaging, as I'm sure many of you are aware of, the goal is to design new, better, and more capable cameras through the co-design of optics and algorithms. So a normal camera usually consists of a lens and a sensor. The lens focuses light from the world, and then the sensor records it. And so then basically what you measure looks very similar to the scene of interest, and little to no processing is required after the image is captured. A computational camera, on the other hand, can use the optics to encode information from the scene. So the measurement might not look very much like the scene of interest, but all the information is there. And for these sorts of cameras, we have the additional step of using algorithms to solve for the scene of interest. This is called solving the inverse problem. And then they'll take you from the measurement to the final object. And with these algorithms, we hope to unscramble the scene and even potentially recover more than just the 2D image. So in this example here, we're actually recovering 3D information from an encoded 2D image. So by designing the optics algorithms together, we can aim to push our cameras to and beyond their limits. But we need to have really well-designed optics and well-designed algorithms to achieve this. In this talk, I'm going to focus on the algorithms and how we can make them better through physics-enhanced machine learning. First, I'm going to start with a simple example of 2D lensless imaging, and then extend the foundation I built there to show a more challenging case of single-shot 3D microscopy. In both of these cases, we're going to need to have a really good understanding of the optics of the camera in order to build in this information into our physics-enhanced networks. So let's begin with a 2D lensless imaging example. So here we have a 2D lensless camera called diffuser cam, and the camera basically consists of a phase mask or a bumpy piece of glass that randomizes the light hitting the sensor. So the measurement looks very little like the object of interest, and then we can use algorithms to figure out what the object was from the measurement. But to do this, we have to understand how each point in the world travels through our camera, and we have to formulate some sort of forward model A. The nice thing about diffuser cam here is that it has actually a very simple model. Basically, if you take a flashlight and shine it through the camera, you'll get this point spread function on the right, which is this sort of wavy pattern. And the great thing about this sort of camera is that if you move the point up and down through the scene, it actually just linearly shifts. So you can say that the system has a shift invariant point spread function. And if you think about a more complicated scene with many, many points, you'll just have this wavy pattern repeated over and over again across the sensor to get your measurement. So basically the measurement is a sum of the point spread function at each point in the scene. Now mathematically, this has a very convenient formulation where we can just say that the measurement is a convolution of the object with the point spread function. All right, so now we know how each point in the world maps through our camera to our measurement. So then we can hope to formulate some sort of inverse problem where we go from this measurement to a guess of what the object is. Now, of course, inverse problems have been around for a very long time, and there's many different ways we can go about this. I'm going to kind of classify inverse problems in sort of 3 different categories. The first are these classic methods, which use optimization to solve this problem with a data fidelity term and a prior. So the data fidelity term, you're going to build in knowledge of your system, and you're going to say that your measurements should be consistent with your imaging model and the guess of the image. So you're going to minimize this quantity. And the second term is some sort of hand-picked prior, which you can pick for your application. In this case, I'm going to say, oh, we want to have sparse gradients. And in general, you want to minimize some sort of quantity that you specify here that is based on your system model, your measurement, and your prior. And I mean, you can do this many different ways using gradient descent. There are many algorithms that go about doing this, such as FISA, and they work really well off the shelf. However, they're iterative, which means that for some of these problems, they take a very long time because you have to do these steps over and over again, sometimes hundreds or thousands of times until you converge to the final image guess. So while these methods work really well off the shelf, they can be very slow. On the other hand, there's been a lot of work recently in deep learning where you don't necessarily have any system knowledge built in. What you do is you instead say we're going to have some sort of deep network, which is going to approximate the entire inverse problem. So you go from your measurement to a guess of the image. And if you have some real ground truth training data, you can compare the image guess to the ground truth and update the weights over and over again for all of your training until hopefully the network outputs a very good image guess. Now, the training phase can be very slow, but at test time, it can be very fast because you don't have any sort of optimization loop to go through. You just have a single forward pass, and you can do this very quickly, typically. The third category is what I'm going to call these physics-informed machine learning methods, where you kind of have the best of both worlds. You incorporate knowledge of the imaging system physics, and you have training data. So if there's anything about your optics that you can very easily model and incorporate, you can do that. And the training data is used in case your model isn't perfect, or in case there are some things you cannot easily model. And so you kind of can refine your estimate and use both training data and knowledge of the system to get back the best guess. And similar to deep learning, the training phase can be very slow, but at test time, it can potentially be very fast. And so one way we can do this is we can actually unroll some sort of optimization problem about a number of times. And so instead of having to converge after, say, 100 or 1,000 iterations, you can say we're going to bound it to like 5 iterations and then just try to get the best image in a bounded amount of time. So let's see how these 3 different methods perform on this example of imaging. So on the top left, we have our input, and then we have the ground truth. So for the classic methods, they produce a pretty good result, but they're very slow. So it takes 1.5 seconds for each image. On the other hand, the deep approach on the right, where we don't incorporate any knowledge of the system physics, is very fast, but we're missing a lot of details. So you can see the butterfly wing here is kind of missing the lines. And one of the reasons here is because we have to basically learn everything from scratch. So you have to just be able to go from this like highly multiplexed image on the left to the ground truth all in one go. And this is actually very, very challenging. So our intermediate approach of physics-informed machine learning, where we incorporate knowledge of the optics that we do know and can easily model, it does quite well because there's less it has to learn. It already has a head start. But we get very good image quality. You can see some of the detail on the wings here, and it's still very fast. So basically, these sorts of methods, as you can see here, are kind of this hybrid approach between the classic and the deep methods, where you get kind of the best of both worlds. You get something that has pretty good image quality, and it can be very fast. All right, so now we want to extend this formulation to single-shot 3D microscopy, which has some very unique challenges associated with it. Now, the goal for this sort of problem is that neuroscientists, they want to study neurons firing in the brain, and brains are 3D. So we want to see things firing in 3D. And of course, the challenge here with a typical camera or microscope is that we don't really encode depth. So if you have a point that's focused onto the sensor, it'll map to a point. But if this point is in front of or behind focus, it maps to the same sort of blurry function. And so you can't tell whether something is in front of focus or behind focus. In our lab, we've tackled this problem by optimizing a microscope to encode depth. And the way we did this is, instead of having a single lens, we designed a custom phase mask, which has multiple lenslets, all with different focal lengths. And so what you get is this pattern as you sweep through depth that changes and has high frequency features throughout the whole thing. So basically, you can encode depth natively with a sort of microscope. And it's very similar to diffuser cam and the fact that like you have this point spread function. However, the difference is now you have this model where you have different point spread functions for each depth. So your forward model now is basically a convolution of your object at a certain depth with the point spread function at that depth. We can do this for each depth of interest, and the final measurement is a sum. However, unfortunately, in practice, this sort of model doesn't quite work. And the reason is that oftentimes in microscopy, your point spread function is not shift invariant. So what actually happens is if you flash a flashlight throughout your system, the point spread function changes quite a bit across the field of view. And this is due to aberrations in the lens. And so this really complicates our math here, because instead of just having a single point spread function for each depth, we now need to have a more complicated model with k point spread functions for each depth. And so we need a lot more memory and a lot more compute to do this, because now we have a whole bunch more point spread functions that we need to calibrate for and use. So with the classic methods, you can do this. You can formulate a low rank model and solve this problem. And whenever you do that, you actually are able to get this encoded measurement, solve the inverse problem, and get back a really nice 3D reconstruction. However, the problem is that now that you have this complicated low rank model where you have spatially varying nature for the point spread functions, it's very, very slow. So it takes about 20 seconds per image just for a 2D image, and 11 minutes per image on a GPU for 3D. So if you're a neuroscientist and you implant your microscope into a mouse brain, it's going to take you 11 minutes before you know whether you're looking at the right thing or not. And this is just too slow to be practical. And this is a big limitation of these sorts of cameras, is oftentimes the inverse problem might take a very, very long time, and it makes it impractical. So in some of my work, we tried to tackle this problem and try to make this really, really fast and real time. So what we did was we created this physics-informed network, which incorporates the spatially varied nature of the microscope. We basically have these learnable filters, And we perform multiple Wiener deconvolutions where each filter is initialized with a point spread function at a different point in the field of view. So what you get back is these intermediate images here, which are sharp in different regions. And then you can use a CNN to combine and refine this. So you get back a single sharp image from multiple images that are sharp in different areas. And this is all very fast because the Wiener deconvolution is a single step. And so we basically, instead of having something that's iterative and very slow, we have like a few small Wiener deconvolutions followed by a CNN. And what this does is that it tries to get the best image guess and does this very, very quickly. So after training, we can do this both for 2D and for 3D images. So for 2D, we're able to get a 600x speed up compared to the classic method. So the classic method takes about 20 seconds, and ours is 0.032 seconds. And we also get pretty good image quality because we take into account the spatially varied nature of the point spread function, so we have sharp features throughout the entire image. If we compare it to the deep method on the right, which has no knowledge of the system, it doesn't do so well. Things are very blurry, and that's because it's having to learn everything from scratch. And we can also compare it to a spatially invariant model, and we have much better features on the outside of the field of view. The speed up is more dramatic for 3D. We go from 11 minutes to 0.41 seconds. And so now we're actually approaching real-time quality. So we can get back this single shot 3D pretty much in real time and still have very good image quality. And of course, we do a little bit better than the pure deep method on the right, which kind of hallucinates information, which you see here. So now, basically, by using these physics-informed machine learning methods, we're able to make these sorts of cameras more practical by improving the image quality and making it potentially real time. So in conclusion, I showed these two examples where we can use physics-enhanced machine learning to improve computational cameras, showing huge improvements in the time. So we have a huge speed up, and also the performance is quite good. You get back very nice image quality. Throughout my PhD, I've also worked on snapshot hyperspectral imaging and low light noise modeling, which is going to be featured as an oral on Friday. So come check that out. And if you want to learn more about my work, I have this QR code on the top right, which has all of the papers and all of the code for these projects. I'm happy to take any questions. Thank you.
Christina, thank you for the beautiful talk. It's really cool to see how this work has progressed through these multiple projects. And I see a bunch of people in the room taking a picture of your QR code. So sorry we can't share the energy of the room with you more directly. If anyone has a question, please feel free to come up to the microphone.
Hey, Christina, great talk. This is Chi here. I have a question regarding the diffuser cam that you present at first. I may have missed that, but could you elaborate a little bit more on how you combine the physics-based method and the neural network together? Thank you.
Yeah, so basically we take ADMM, which is the classic method we typically use to solve this sort of problem. And we can actually unroll it. So normally for this, you have like multiple steps with an ADMM that you do over and over again until convergence. And this problem, what we do instead is we unroll it and bound it to a small number of iterations with some learnable parameters throughout that, followed by a UNet at the end to further refine the image. So you basically have some like bounded physics-based compute followed by a deep network that will improve the result. And that's kind of how that's formulated there.
Gotcha. So you basically early stopped your ADMM iterations and use a UNet to do the rest of the optimization and find that to be very effective, right?
That's right. And the hyperparameters within ADMM are also learned and optimized for this too.
Gotcha. Thank you so much.
Hey, Christina. Nice, great talk. I had a question that was not directly related to your presentation. It was more about lensless imaging. So if you look at a macro scale, if you have a very bright light source in a lensless imaging system, what will happen? It will basically saturate the whole image compared to a lens system. So do you have any thoughts about something like HDR in lensless? Are there solutions that are possible?
Yeah, I think that's for sure a big issue with these sorts of cameras where, your dynamic range is reduced a whole bunch because you spread the light to a whole bunch of pixels. I think that perhaps if you have some sort of custom design where instead of spreading the light across the entire sensor, maybe you spread it just enough to get the things that you want to do. Like for instance, if you want to encode 3D, you don't need to spread the light across the entire sensor. You can perhaps confine it to a smaller region and still have some sort of encoding that you do. So I think there are potential solutions. But yeah, it's definitely a big challenge with these where, if you spread the light, you're going to be vulnerable to the fact that if you have something very bright, it's just going to oversaturate everything.
Thank you.
All right, I know there are many people who have questions, but we are already over time. So I'm going to take one last question from Payman on the call, and then we'll switch to our in-person workshop. So thank you everyone who's on the Zoom call. Payman, take it away.
Well, thank you, Christina, for a very nice talk. I was wondering if there's any way that one can tell how much of the work in solving the inverse problem can be attributed to the unrolled network versus the UNet. Like how important is each piece?
Yeah, so I would say in this case, we have a deconvolution with a very large point spread function. And so the unrolled part does a good bulk of that. So we can look at it, the intermediate result after this step here and kind of see what goes into the UNet. And in practice, what it looks like is it looks a lot like the butterfly, but it's a little bit noisy. So I'd say the UNet does a lot more of the denoising. And the thing about these sorts of cameras is we have a lot of structured noise do the deconvolution process itself. So we have a lot of these like line artifacts and streaks throughout the image. And what the UNet does is it kind of cleans that up and gives us something that looks a lot more like the lensed images that we have.
Makes a lot of sense. Thank you.
Thanks.
Okay, and with that, thank you everyone on the call. We're now going to transition to being totally in person, but we hope to see you all at CCD next year. Thanks again, Christina.
Thanks.
And on one hand, this can significantly reduce the cost and also the complexity of the equipment of IDT. But on the other hand, it will make the reconstruction problem in IDT much more difficult than the classic ODT, because now the problem is a phase retrieval problem, and it cannot be characterized by the classic linear Fourier diffraction theorem. So similar to ODT, IDT acquires a set of measurements to do the reconstruction. So these intensity measurements corresponding to different illuminations of the same sample, but from different angles. So by programming this light source pad, which is LED, we can generate different illumination patterns, which each of which leads to a different coverage of the Fourier spectrum of the sample. So common illumination patterns include dense, annular, and multipixel. Here shows the optical transfer function corresponding to each illumination. So overall, the goal of IDT is to reconstruct a 3D refractive index RI volume from the 2D intensity measurements. So this is actually the problem setup. So here the refractive index RI defines the optical property of the sample. So it actually characterizes how the sample interacts with the light. So it's a complex number. So the real part corresponds to the phase information of the sample, and the imaginary part corresponds to the light approach. And also so by reconstructing this RI volume, we can retrieve a morphological structure of the sample we desire. Okay, so we adopt neural fields, NF, to solve this problem. So here's a quick intro to neural fields. So neural fields is like really hot topic right now in CD, and there's a dedicated workshop downstairs in Hall D. If you wanna attend, go to that workshop, please. It's very crowded, so please go there right now. Basically, the key idea of neural fields is like it uses a new deep neural network to represent a physical field. So one famous example is the neural radiance field nerve. So by mapping the spatial coordinates to the altitude, which is the power and density, it actually encodes this neural radiance field or the object into the weights of the neural network. So it's no longer a discrete representation that's based on vectors. Now it's a continuous or neural representation that is based on the neural networks. So also, like in nerve, they're solving a problem of multi-view synthesis. So like they can learn a 3D, the neural representation of a 3D volume from multi-view 2D images. So we can see the similarity between this problem and the image reconstruction problem in IDT. So it's both 3D reconstruction from like multiple 2D images. So this similarity actually motivates us to use neural fields. And beyond this simple reason, there are several other reasons that motivates us to use NF. First is that the neural fields is like self-supervised learning method. This means that the model only needs the measurements or the data associated with the testing sample itself to train. So it doesn't require external data like a huge set of biomedical or biosample images to train model. Just use the testing samples. And second is the multiple work has shown impressive results of NF on several computer vision tasks. So these empirical evidence suggests that NF may also achieve very good results on the IDT reconstruction task. So lastly, I feel this one is most interesting. It's like the neural fields enables off the grid continuous representation. So I think it's a very interesting way. And also it's related to the fundamental aspect of image processing. It's how to represent the image. Like in old times, we just use vectors to represent the image, but now we can use neural network to represent the image. And the representation is fully continuous. So due to these reasons, we propose deep continuous refractive index field, DCAF, as the first NF method for this computation across the modality. So DCAF overall has 4 features. So I will illustrate one by one. The first feature is that the backbone of the DCAF is a multi-layer perceptron. So different from the convolutional neural networks, the DCAF takes the spatial 3D coordinates as the input and maps these coordinates to the RI values, the refractive index values corresponding to these coordinates. So via this training, the neural network itself becomes a representation of the volume waveforms. And I call it like, or people call it neural representation, or continuous neural representation, coordinate-based representation, names go on. So because right now this representation is continuous, we can actually do some like a interesting post-reconstruction manipulation on the volume. So we can actually create a denser grid to the neural network to retrieve a like high pixel resolution volume out of it. So here the example shows we do a 30.8 times pixels of resolution, and you can see how well this kind of structure of the sample is preserved inside the neural network. So the second feature of DCAF is like we can infuse the physical model into the model pipeline. As talked by Professor Payman, Professor Milanfar and Christina, like fusing the neural networks and the physical models are kind of hot in our field because it combines the benefits of both sides. So DCAF or neural fields also shares this kind of property. Here shows the physical model we used in this IET problem. It's so in short, it's a linear forward model based on first order approximation. So one thing I want to note that is DCAF is not limited to certain forward models. So if you have a more complicated, more like fancy forward model, you can just use it and plug that in. And by using this physical model, we can actually enable the loss evaluation directly on the measurements of the test sample itself. So we don't need to, so the supervision fully comes from the intensity measurement, the images. Because we use the physical model to project the predicted volume into the measurement domain. So the third feature of DCAF is that we propose a novel encoding strategy to represent the oriented features. So here is a brief introduction of this encoding in neural fields. So empirical evidence indicates that coordinate-based MLP cannot actively capture the high frequency information in the image, so they are reluctant to these kind of information. They only capture the low frequency, which is the general structure of the image. So in order to force the MLP to capture the high frequency image, we need to manually expand the input coordinates as a combination of the low frequency parts and the high frequency parts. So in this way, the neural network can learn or capture this high frequency information. So this is called encoding or positional encoding. So currently the most popular encoding strategy is the positional encoding, and it's proposed in the NERF paper. I think it's one of the, it borrows the name from that, like a natural language processing from this like transformer models, and they regave them the name of positional encoding, and they used it here. So the idea of positional encoding is very simple. It's just you doing a 1D Fourier series type expansion of each x and y or z axis. So these axes are orthogonal to each other. However, in our experiments, we observe that because of this orthogonality, it cannot represent the features that oriented that does not lie on exactly along this axis. It's oriented features. So to solve this problem, we propose radio encoding, and the idea of radio encoding is pretty straightforward. It's like before you perform the positional encoding, you just first rotate the coordinates by multiple angles, and you do this 1D positional encoding to each of them. And then finally, we can have a radio pattern like coverage of the image. So here shows two examples. So this is the results obtained by positional encoding, and this is the results obtained by radio encoding. We can see inside this ball, there's some like oriented winkles. As it cannot be represented by positional encoding, but it can be represented by radio encoding. So the last feature of decaf is the synergistic integration of the internal and external regularization. So one way to view neural fields is like you can treat it as a new variant of like deep image priors or similarity to deep image priors. So from deep image priors, we know that the structure of the neural network can provide internal regularization. So we observe this effect or phenomenon for the neural fields as well. So here shows the results achieved by only using the encoding class MLP without any external regulation. So you can see this already provides better results over the classic or traditional Tikhonov regularization. However, we observe that this is only for the thin samples, meaning that the physical model can well explain the real physics, and the light really like bends only once. But if it comes to the 6 samples, meaning that the 4 model we're using more or less cannot explain the real physics, which means that like there's multiple scattering happening inside the sample, then the encoding plus MLP will completely collapse. So in order to stabilize this neural fields, we introduce external regularizers, and the expressions shown here is like a 2D noise reduction inspired by the denoising priors and a 1D axial continuity. So these two terms together forms a 3D volume regularizer. So by using this regularizer, we can see that the performance of decaf can be significantly. So next, let's see some quantitative results. We generate a granular size phantom to do this. Here shows the approaches. You can see it's like these here and there. In the right figures shows the results obtained by decaf and the 2 baseline methods. So the first baseline method is called the SIMBA, which is a regularization by denoising based approach. And the other is the Tikhonov regularization. So in the zoom in, I think in the zoom in volumes, you can see this more clearly. decaf obtains a much sharper reconstruction than the SIMBA and the Tikhonov, especially along the z-axis, which is the optical axis. In SIMBA and the Tikhonov, we can observe clear elevational artifacts, while in decaf, kind of well mitigated. This better quality is also reflected in the numerical values like PSNR and MSE. So over SIMBA, decaf improves the PSNR by 1.6 dB, and over Tikhonov, decaf improves by 3.4 dB. Here is some experimental results on real bio samples. So first one is the dysomology. So in the right up corner, you can see here it shows which depth you're at is showing here, and the figures at the bottom is the lateral view corresponding to this dash. So you can clearly see that decaf gives better sectioning effects over the standard Tikhonov regularization. And also, when you look at the lateral views, the missing cone artifacts is significantly removed without touching the general, the key structure of the sample. And also, let's see. And also note this smoother transition in the Z-depth is because we use this continuous representation to interpolate the missing axis. Here shows the pixel super resolution for the XY plane. We compare with the nearest neighbor bilinear bicubic. You can see the, I don't know if you can see clearly, there's some like jumps here pointed by the arrow, but here is like smooth transition. This is another example for the human pupil cell. You can see that the cells are like overlapping with each other. So in the Tikhonov, from the lateral view, we can, it's barely to see if the cells are like clearly separate. But for decaf, the two cells are, there's a clear separation between the two cells. And here shows the continuous interpolation along the Z dimension. So the red numbers means that these are the coordinates on the training grid, while the other like random numbers are interpolated. So you can see the smooth transition of this bacteria cluster. Okay, lastly, I will present one showcase of the thick sample, which is the C. elegans form. Similarly, you can note the sectioning ability of decaf. Here shows the lateral views here corresponding to the top. The missing cone artifacts is well excavated. Okay, this is the end of my presentation. So here shows all the co-authors. Thanks to co-authors. Thanks. Thank you.
We can take a few questions. Hi, great job. You have really nice results. I'm wondering how long, if you say something about runtime and consistency of things that.
Oh yeah, sure. So the training time for decaf is about, it varies for samples. For the smallest sample we have, it trains for 2 hours. It's roughly 400 by 400 by 40 slices. And for larger samples like the C. elegans, like it's 1,000 by 1,000 by 60, I think. So it's trains for like 6 hours. Yeah. So, and also for moving, yeah, I think that's a very good question. So for the moving things, currently we didn't explore it, investigate this in our work. But we try some like initial like tests. We feel there's another paper like on Cure we submitted to this. So we show that vanilla nerve cannot will represent the moving objects. Yeah. So I think extra prior knowledge is required for that.
You said your forward model was
The forward model as well.
It was the forward model, the first order.
Yeah, exactly. So based on first form.
Were there any kind of artifacts that you saw that were there that you?
Oh, I see. I think this is a good point. So we use this first order model mainly due to the computational efficiency. We didn't try second order or higher order of formals, but I believe that by increasing the capability of the formals, we can enable better results.
So let's limit maybe to 2 questions because then we go for lunch. We go with 1, and I think you were the second. Yeah, go ahead.
Oh, why I'm choosing MOP, right? Okay, so the reason I'm choosing MOP is into this like coordinates. So it's basically like the X, Y, Z three values. If you it's difficult for me to adapt this for convolutional methods. Also, for now, like in the newer fields, it's on the standard to use MOP. I know that question. Okay.
Just one more, by the way, then any other questions can be taken offline because he's physically here. You can really discuss this thing. But unfortunately, we'll just take one more. Go ahead.
So you said you do radial and it's a radial and station coordinates.
Oh, this is radio encoding is for the spatial coordinates. So it's just the your first rotates the coordinates and then you perform normal positional encoding.
I'm just importing the same concept.
Or sorry, I didn't hear you.
Are you just making it more?
Oh, I see. So I think this is related to a like paper called Fourier features like the NLP principle. That's the name of the paper. So in that paper, they said instead of doing positional encoding, you can just multiply the coordinates with another like big matrix